All right, great to be here. And yes, as it was mentioned, I'm going to share a demo that I like doing with my students, and it's related to atomic physics. So moving on this timeline, right? Rutherford famously did some experiments about 100 years ago, a little bit over that, that started giving us some idea about the atomic structure. And with his gold foil experiment, he came up with this planetary model for the atom, right? Which looks a lot like the picture that we see in regular textbooks. So I think we can see that picture in the slide as well, right? But then people quickly figured out that there were some problems with this model, as we can see in the next slide. So just from the way the electrons are supposed to be moving, you would expect it to be continuously emitting radiation and losing energy, but most of the atoms that are around us are stable. And also when they started looking into atomic spectra, like we can see in this picture, they realized that the light coming out of atoms when you excite them is very strictly limited to some colors and not others. And from the model, you would have expected a rainbow. So it was like a mystery that people had to solve some time ago. And so the demo that I use, it's relatively simple. So you just need to get some diffraction ratings. For example, you can get some at Amazon, and these are just pieces of plastic that work like prisms. So they can split the light into its constituent colors, right? So for example, here in this picture, you can see me holding it close to my eyes, and you can see like lights on the room and see what are the colors that are made out of. Um, so the main thing, if we go to the next slide, is that you can get a power supply, really from Amazon, for example, and some discharge tubes. So these are glass tubes that are filled with some gases, for example, hydrogen or helium, and they have electrodes. So you can run current through it, and they will start glowing with some very characteristic color. And then by using the diffraction rating, you can split the light and really see how does this spectra look like. All right, so then maybe let's go to the next screen. So now I'm going to try to demonstrate the demo just right now. So the first thing is I'm just going to turn on the LED light of my cell phone, and then we can try to see it through the diffraction grating just to see how it looks. So usually this is fun for the students. So I'm just going to put it over here, and then uh, by looking through the diffraction grating, I think we can even see it through my camera. Um, so, right over here, you can see that there's a full rainbow, right? So you can see all the colors, which is what people were expecting it was going to come out of the discharge tubes, for example. So let me switch to one of the tubes right now. So usually kids like doing this a lot just because it looks really pretty. So I'm going to put the tube over here and dim down the light, and then we should be able to see the spectrum as well. So, all right. So then I'm just going to energize it. So then it's going to start glowing. And you can do this with your students as well. And let's see. So you can clearly see that it has a very nice spectrum, right? So you can see the lines, and this is a picture that you see in textbooks, but you can really see it with your own eyes. So it's really nice, and you can try just different tubes. Right. So just like this, like you can even do it on Zooms, right? So it's so simple and it's relatively cheap. So I'm just going to turn it on, and maybe we can just go back to the presentation. So really, you can get all of these for about $400, and then you have a whole setup that you can use with your students. And I think it's really nice, and it has a really strong visual component. So maybe we can go back to the slides, if possible. So I have done it with many people because it just looks really nice. It even works, say, with first graders. I have done it with them, and I mean, it's you have to adjust what you are explaining, of course, but it just looks so pretty that the kids like it a lot. So then let's just go show the other points in the slide. Right. So then as I said, it's just really engaging almost all the kids like it a lot, and the cost is relatively low. So in terms of the key ideas that I like to highlight with my students, right? Like these spectra are unique barcodes, so they're very similar to fingerprints. So for example, this is how we realize, if we show the next text, that's how we know that the sun is made of hydrogen and helium, right? It's too far and too hot to go and take a sample, but you can analyze the light, and that's how people figure that out. And that's also how we now know, for example, that what is inside the atmosphere of some exoplanets. So that gets kids really excited. And in the next slide, right, this is something you can see with your eyes, and you can see that it has very discrete lines. So then basically this is telling you something about the atoms, right? So for example, if you see neon, it's an atom that is much bigger. So then that's why the structure is much more complicated. So then it's just a direct visualization of that. And in a way, this is exactly what people looked at 100 years ago when they started figuring out quantum mechanics, right? So then you can feel exactly like what they felt some time ago. So I really like this demo. I think it's relatively simple and easy to set up, and you can do it. So I like it a lot.
So if we think about room temperature, 300 Kelvin or, 80 degrees Fahrenheit, to absolute zero, which is the coldest possible imaginary temperature where all molecules stop moving, as a scale of football fields, around 1 foot from the end zone is where we have the coldest naturally occurring thing we've ever found, which is the Boomerang Nebula. It's at around 1 Kelvin, colder than the microwave background radiation. And then at less than a millionth of a Kelvin, we have what I work with, which is Bose-Einstein condensates, or BECs. In our football field metaphor, this is the difference between a foot from the end of the field and touching the end zone, essentially. And so what exactly is a BEC? As you probably know, matter is both a wave and a particle. As Young's double slit experiment showed, he sent light through 2 slits and managed to get an interference pattern, which showed that light acts as a wave. This experiment has also been done with electrons, and we see this same interference pattern, which shows wave-like behavior. And what those waves are kind of complicated, waves of probability of location. But the main thing is that we can describe particles by waves, which, if we can transition to the next part, as those atoms get colder, their wave functions get larger. And if we can get them cold enough and close enough together, those wave functions will start to overlap. And when that happens, we can form what's called a Bose-Einstein condensate, where particles stop acting like individual particles and start acting as one wave. And in order for that to happen, the atoms, like I said, must be very close together and very cold. And the ways we accomplish this, Doppler cooling and evaporative cooling, have parallels that you can see in your own daily life. So you probably know of the Doppler effect. If you move towards a source of waves, it will seem to be higher in frequency. And if you move farther away from a source of waves, it will lower in frequency. This is why when a siren passes by you, as it comes towards you, it gets higher in pitch. And as it goes past, it gets lower in pitch. And this also happens with light waves, which allows us to use them to do really cool and interesting things. So the first step in cooling atoms to reach a BEC is what's called a magneto-optical trap, or a MOT. Essentially, we have 6 lasers intersecting at a point, and all of the lasers are shifted down from the frequency that the atoms will absorb. As Danyel talked about, atoms have very specific characteristics. In the top corner, you can see the absorption or the emissions for rubidium. And those 2 peaks right there are the resonances of light that rubidium will absorb. So we use that D2 peak right there to cool rubidium atoms to condensing temperatures. Because all of our lasers are slightly shifted down from the necessary frequency, as atoms move away from the center, they will see the light at the frequency they absorb. So only moving atoms will absorb that light. And we use a magnetic field to keep the atoms near the center. So we enter the next slide. When atoms absorb light, we'll have a momentum transfer. Light, as you recall, is also both a particle and a wave, and that momentum transfer causes atoms to slow down. The analogy someone in my group likes to use is like shooting a water cannon at an ice skater and to push them into the center of the rink. As soon as an atom moves away, they are forced to absorb light. And if you can click, so the animation will work. As they absorb, they will move backwards. And temperature really is just a measure of kinetic energy. So as atoms slow down and are pushed towards the center, they will both get closer together and start to cool because they have less kinetic energy. But there is a limit to this, called the Doppler limit, at which point absorbing a photon will cause it to heat. And when we reach that, we need to use what's called evaporative cooling. This allows us to let the most energetic atoms escape, so the total sum of the atoms becomes colder. Essentially what we do is we have all of our atoms trapped in that shape right there, which is called a harmonic trap. And we slowly lower the edges so that the most energetic atoms can escape. As that happens, the cold atoms remain close together due to the trap, but the overall energy is less, and therefore it cools down. This is the same reason why you might blow on a cup of hot tea. When you do that, all the atoms that are very hot are close to steam and will rise to the top of the drink. So when you get rid of those, the whole of the drink will be colder. And we can do the same thing to reach the temperatures needed for condensation. All of that requires all of this very crazy looking equipment. That's our setup before the updates we're currently making. So all of those black parts are lenses and mirrors meant to make our lasers very tightly focused in the right shape. And those big red coils over there make our magnetic fields that allows for our trapping. And from those, we can create items like on the right, which are real Bose-Einstein condensate photos. The condensates in that photo are about the width of a human hair, and we can take those with just a normal camera. We have to use lenses to focus it, of course, but it doesn't require any, special microscopic cameras. We can see these with the naked eye, but they act as a singular particle. Of course, this is less than 99% of our atoms that we started with, but that's how it works. All right, so that is the end of my talk.
So I'm going to present the quantum enigmas that were developed here at the Quantum Institute. Next slide, please. There are a series of animated video introducing people to the concepts of quantum physics that are necessary to understand quantum computing. So quantum gates and how to build circuits and what they represent exactly. With a focus on solving real problems that are introduced in these videos. Next slide. The only requisite to understand this series is to watch the first video with the required notions. That's where you're introduced to qubits, what they are, which is actually the unit we use in quantum computing, in contrast to the classical bit, in classical computing. Next one. And we have a lot of videos, and they go in ascending order of complexity. So the first ones are don't have any quantum advantage. They're mainly to introduce the basic concepts and how we can play with things like superposition and entanglement to actually solve a problem. So the level is a bit easier to start with for high school students, but if people are more interested, they can advance and get a higher understanding by themselves with the material. Next one. So I would like to play the first part of the first enigma, the treasure door, so you can see what it looks like. I hope it works.
You are walking towards your destiny when suddenly you come across two doors. Behind one of the doors lies a treasure, but you don't know which one. There is a guardian in front of each door, and both know where the treasure is. One of the two guardians always lies, while the other speaks the truth. You don't know which one is lying or which one is telling the truth. Both guardians know which one is lying. Your challenge: ask a single question to one of the two guardians to find out where the treasure is. You can press pause to think about it or listen to the answer now.
Yes, so as you see, the format of the videos are that at first there's an introduction of an enigma or a problem. For this one, it's the treasure door with the guardians. Most people know the answer to that one, but it's interesting how we can actually build a quantum circuit to solve it. And so afterwards, after the problem has been introduced, there's a short segment that solves the enigma. So if you could play it for me.
Guardian, tell me not to open. Explanation: both of the guardian answers are always the opposite of each other if you ask, which door is the treasure behind? Or alternatively, which door is the treasure not behind? This statement is no longer true if one asks, which door would the other guardian tell me not to open? With this question, both guardians give the same answer, the right one. Let's suppose the treasure is on the right and the right guardian is lying. If you ask the one on the right, which door would the other guardian tell me not to open? He'll lie and answer, the other guardian would say not to open the right door. If the left guardian is asked the same question, he knows the right one is lying and answers, the other guardian would say not to open the right door. To translate this problem...
Thank you. So I see I'm running out of time, but I'll try to finish quickly. So yeah, we have the solution, and the last segment of the video is how you can build a quantum circuit to actually code how the solution is produced for every possible combination of who is lying and who is not lying. So quickly, the last steps, I wanted to mention that we have a lot of coding exercises that are all free of access, and they're through the IBM Skills Build module that people can go to. So after they watch the video, they can practice what they learned and also go further and code with an actual library that's called Qiskit that we actually use in research right now.
So what I wanted to share with today is an answer to the question that I had to think about in terms of, how do you teach quantum to somebody who doesn't know anything about quantum in a way that's hands-on, that teaches concepts that are really foundational to quantum and is exceptionally cheap and could work in a country that doesn't have, let's say, reliable electricity. So we saw a really nice demonstration from Danyel before, which is like $400. So my demonstration costs $4, all right? And all you need is one of these, which is a sheet of polarizing film. So for those of you, you can find them multiple places, but I'll just put one of the link, like on Amazon. I think I got 3 of these for about $12. So the polarizing film, I have a bunch of other little sort of props and demos, and in order to see them more clearly in your view screen, it's probably better to put it in the upper right, to put it in speaker mode, so you can see me more clearly. You can see the demos. So you can do this as a demo with a big sheet. Sometimes people do that. If you've seen cross polarizer experiments or demonstrations before, it's basically the same thing, but it's using a quantum explanation to understand what's going on. I like to do hands-on activities. So what I do is I take this and I cut it into just small rectangles and pass these out. And then individual students or whoever you're talking to can have these. And so if you look through these, and there's a bit of reflection from my screen, so it's hard to see not much happens. You see the light is cut down. There's a bit of an effect that you might be able to notice near where the reflection off my cheek is, where if I turn that kind of goes away. And that's a pretty subtle effect. But one thing you can find now in a lot of environments are screens. So that's why these screens behind me, these are not always there. And if you hold this up in front of one of these screens and you turn this, you can see some interesting things like the light being blocked completely. And that's because there's polarized light coming from the screen. Different screens are different. I have a MacBook screen down here, and you notice it's like purple, and then it turns to sort of yellow there. And that's because the different colors are polarized differently. So in terms of explanations, what I usually talk about is first like light quanta, the fact that light comes in quanta, and those individual light quanta look something like this. So this is not exactly what they look like, but this is a red quanta. So all red light comes in little quanta of energy that are some size. And if you go up to yellow quanta, they're bigger. And if you go to blue quanta, they're even bigger than that, more and more energy. And if you go even higher, you get to like UV quanta. And this is why you can get sunburned by the sun, is because there's big UV quanta coming from the sun. So I think one of the things I really like is grounding quantum mechanics. It can sometimes seem abstract, but just the fact that people get sunburned is an effect of quantum mechanics. So the key thing about this model of individual light quanta is that if you imagine light, like blue light coming this way, this can have an orientation to it, right? And this is the polarization of the light or the polarization of the individual photon. So there's many different types of polarization. I'll just be concentrating on linear polarization. That's all this demo really talks about. And so you can rotate this to show the different polarizations of light. And so this is an example of a quantum bit that Isabelle just talked about. So a single photon, its orientation, its quantum state is basically just what orientation it's at. There's infinitely many orientations it could have. But when you measure what its quantum state is, which we'll do in a minute, and that's what the polarizer does, you get, in this case, one of two answers. So you get a binary answer, and that makes a quantum bit. So when you're thinking about qubits, quantum bits, this is an example of that. And so what is this doing when it goes through? Well, here's my model of what this looks like at the microscopic scale, which is you have the photon coming in, the light, and if it's oriented this way, it can go through. If it's oriented this way, it won't go through. And if it's oriented at any angle between, there's some chance it goes through. So if it's a 45-degree angle, it can sometimes knock its way through with a 50% chance and sometimes get stopped. The actual probability depends on the cosine squared, which is the same relation that's in Malou's law, which you may know from E&M explanations of polarization, but it's a single quanta and obeys the same statistics. So the basic demonstration is just sort of thinking about how the individual quanta, maybe of different colors, go through polarizers. And so this is an example of a quantum measurement, right? The state, this is the measurement. There's a probabilistic outcome to the measurement, and I usually just use 100% chance, 0% chance, 50% chance in demos. Then the other aspect is that when you make the measurement, the quantum state can change from this to this or to something else. So then you can move to actually play around with the polarizers. So I usually hand these out, have people play around with them, see what you see. I have a sort of special holder for these that makes it easier to show things. So sometimes you see this sort of light effects like this from ambient screens. And then you can do exciting things like add another polarizer. So if you add one more polarizer, not much changes. But if you start to turn it, then you see that the light is not as reduced. And that's because the light going through the first polarizer, the individual photons are in one quantum state, and then they're partially blocked by the next one. And so this in itself is kind of interesting. Then you can do the full blocking at 90 degrees, or see that there is basically no difference between having one and two if they're aligned. You can also, with this, put in front of these screens and see some interesting effects like this, which you can take a little time to think about. If you don't have a screen, you can add in a third polarizer and see this sort of cross polarizer effect. And here you have three polarizers in a row where you can see through the middle. But if I take the one in the back and I put it in the front, you can't anymore. So just thinking about the order of the polarizers and the different quantum states that they go through is a really good way of making quantum sort of a hands-on thing that people can see and people can understand the basic concepts. And if I add in, let's see, one more, you get a nice sort of kaleidoscopic effect, which as you rotate things around, you get different patterns for what people see. So this is something that also I think the aesthetics of it are really nice in the sense that when I'm teaching lessons, often I find like young kids don't necessarily remember the physics I want to remember, but they do remember the sort of cool visuals. And if they can just associate that with quantum, that's a great starting point, which they can come back to later in life. So thank you very much.
I've developed apps for so to visualize science and math topics, and so we call them MARVLS. MARVLS are manipulable augmented reality visualizations to learn spatially. That's the acronym. We have a set of 4 apps for mobile devices on the App Store and Google Play Store. It allows students to visualize abstract and 3D concepts in science. We use a merge cube, but we include a template to make your own. So the apps are free and the template, costs whatever it takes to print. We suggest you print it on cardstock, cut it out, and tape it up. And all you have to do is point your phone at the merge cube, and the object the 3D object will appear over the merge cube, and the object actually stays with the cube. So that way you get kind of object permanence, and you hold it as if you would hold something real. Next. Here are some examples of students using the app and the merge cubes in class. And there's an example of me. I blew up the merge cube, and sometimes I'll use that in class as a demo. So you can use it both in class yourself, and you can also have students using it. Next. So how can you use it as a demo in class? It's easily projected from your phone or iPad or tablet to a projector. We have lessons that walk students through selected models on specific topics in the apps. They can be used as in-class activities, as homework assignments, and as extra credit assignments, or just extra resources. We've used all of them that way. And we have developed lessons for them. And so for some of the apps, we're still under development. But I have a link, and I'm assuming that'll be shared with you. Next. So I just wanted to show the 4 apps and kind of Google or QR codes for each one. And then what I was going to do is show it to you live. Hopefully that'll work. So if you want to go, so just go back for a second. Sorry, Nicole. Yeah, so the one that I'm showing first here is the Plasma Physics app that we developed in collaboration with APS for Physics Quest 2024. And we're also developing an app for the quantum computing for 2025. So I may be hitting some of you up for some help. Next. This is the physics AR for Physics 2. So this is developed with the support from National Science Foundation. And we cover all the topics in Physics 2. Next. And we also have one for Physics 1. And then finally, we have one for chemistry that was developed by one of my students because they love chemistry. And so she developed, go ahead, next. Develop one for chemistry, and there's a whole section on organic chemistry, which I know nothing about. And so if you want to share your, allow me to share. So these are the apps on my phone. And so I'll open the Plasma Physics app first. Okay, and you can grab one of the, you can grab the link there to get the merge cube, but we'll go back and I'll just show off some of the plasma examples. I think this one's fun. The aurora, just some information, and then you can see I can hold it in my hand, but I've got the sun, the earth with the magnetic field lines, and we can shoot a solar flare. Right, and just show the magnetic field lines, or the magnetic field is protecting the earth and creating the aurora. We have one for the fiery sun is always fun. So it shows the electric field of the sun, and then the magnetic field. You can see the magnetic field, and you can hold it, turn it upside down. And we have an example here for the tokamak, if you're interested in exploring nuclear fusion. So we've got the tokamak, right? And so we can turn the plasma on and off. We can turn the currents, the B field, the different magnets, right? So the toroidal coils, the poloidal coils, and then the solenoid. And then we have supporting examples for that in the app. But I also want, I'm just looking at the time and I can't tell the time. I'll just show you
a minute and a half. You're good.
Okay, cool. Okay, awesome. So I just want to show the Physics 2 app, which we've done probably the most development with. And if we show you the magnetic field of a magnet, right? So we can look at that and see the density of the field lines right at different points. I'll show another one here of let's do current carrying wire. So here I can turn the current on, right? And we can see the current flowing, right? I can turn it upside down. I can turn on a 2D representation from a book. So you can see like the dots and the X's, and then I can also turn on with this button. I can show like the relationship of what you see in the 2D image, right? And the arrows, and then you know, it keeps it's correct to both sides. And then the other thing that I can do is turn that off. I can turn on the right-hand rule. So we find that students a lot of times aren't accurately using the right-hand rule. So we have examples in each of these that you use the right-hand rule, how to use it for each of the models. I'll show you, let's see, the Physics 1 app, since some of you probably are teaching more Physics 1 than Physics 2. You can see one of the ones I love is circular motion, because I always find it difficult to really explain to students, like, why do we draw the free body diagram like we do? So if I turn on the 2D drawing, you can see that we can line up the 2D representation with the 3D model and then show all the forces, gravity, and we can turn those on and off. I think that's all I've got. I don't think I have anything more in the slides, so I'll stop there.
We have this concept of how scientists look like. I think scientists are always very confused because we are curious human beings. We want to know more. And, you know, on the cutting edge of research, we are always like on the junction between what we know and what we don't know. We are trying to learn more about nature. And so in one sentence or one phrase, like if somebody asks me what is physics, I would say it would be the studies of how stuff works, which is matter, and how does it interact with each other due to the energy. So the interaction of matter and energy is what physics is, in my opinion. Next slide, please. Yeah. So the thing is that, you know, when we look at, so if we look around us, we always see like solid, liquids, or gases are the most common things. You know, so basically, if we ask what are the different states of matter, and as we change the energy of the system, at very low energies, you have solid, which are like, an example is ice, that you have particles fixed in like a lattice structure, and all crystalline solids are like that. Now, as you increase the energy of the system, you get into the liquid state where, you know, molecules can move across each other, and, you know, fluids take up the volume of the container it is in. And then as you go into more energy, put more energy into the system, it, you know, the solid becomes a liquid, water, and then that becomes water vapor, which is the gaseous state. And in the gaseous state, you know, its particles are free to move. There are large interparticle spacing between them. And these are the three common things we look at. We get like all around us. But if you keep on increasing the energy in the system, even like steam at one point, you know, the molecules will start dissociating. It will, you know, that will be the realm of chemistry where molecular bonds are broken. And even at higher energies, you will get into this phase where you start ripping off an electron from the neutral molecule, and you are left with a positively charged ion. So that's called the process of ionization. So when gases get ionized, the properties of that system become so different, we cannot keep on calling them a gas anymore. You know, again, if you think very naively, why do we call solid, liquids, and gases as different? Why do we give different names? It's because their characteristics are so very different. You need different rules and different methods of physics to study them and understand them. So plasmas are ionized gases, but the properties are so very different than neutral gases that we study them, you know, as a field of physics. And next slide, please. And then again, you know, as I said already, like, okay, let's see. If this was a in-person thing, I always ask, like, if we can give examples of naturally occurring plasmas, and due to lack of time, I'll give you the answers, kind of. So the next slide, you know, is the aurora borealis and aurora australis. And actually, we are having a something called a solar maxima, when the sun is spewing out a lot of solar flares. And every day almost, well, every now and then, you are hearing news. If you go to like any like Google articles about solar flares and aurora, we are getting very strong solar flares, and hence even deep down south, like about a month ago, we saw auroras from Alabama, which is like mind-blowing. I mean, I never thought about that. So usually, but if you're in like, you know, West Virginia or even North Dakota, South Dakota, Michigan, and this is the great time to actually see auroras. Sometimes the city lights don't allow us to do that, but if you have a little camera, like a cell phone camera, you can catch them. So they are actually plasmas which come from the sun all the way to the earth. Michele had a nice demonstration for that. The other one, which is more common, is lightning. So you have lightning and aurora, and then, but as you go beyond the earth, the sun is a ball of plasma. All the stars is nothing but plasmas. The interplanetary galactic medium is full with ionized gases and hence plasmas. And then, so everywhere, starting from the lightning all the way outside the extrasolar, it's full with plasmas. Then if you go to the next slide, please. And so again, the question is then why are they so rare on Earth? And why do we care? The answer is it's rare on Earth because Earth is too cold. The Earth is not as hot as the sun. Thankfully, we are all alive, happy and peaceful, hopefully peaceful. And but then artificially, like if you go into the laboratory, if you go to the industry, plasmas are heavily used in the industry. The plasmas are the reason why we can build cell phones. Like the semiconductor etching industry, they all, like if you go into a company like Intel or ASML, you will find hundreds and hundreds of plasma devices. And in the 1970s, 80s, and 90s, the plasma manufacturing industry came up, and hence the cell phones became smaller and smaller. Well, computers become smaller and smaller until you got computers which are, that can fit our pockets, basically, right? And so there are many examples of plasmas in the industry. I can talk about that more. But if you go one more slide, like in our lab, we use something called dusty plasmas. And that's like, what are dusty plasmas? That's what we do in Auburn. Is basically in a plasma background, if you have tiny little solid particles, which is floating in the background plasma, it will interact with the ions and electrons in the plasma, and it will get charged. Those little tiny dust particles will get charged. So next, yeah, please. And you see these different kinds of strange formation. Like this looks like, I don't know, like an amoeba or something, but this is like just dust particles floating. We are shining a laser sheet. So you can only, is basically a cut through our dust cloud. This is just like as if cutting a pancake kind of. And next slide, please. Next, yeah. So dusty plasma, anywhere you find plasmas, all the way from the solar nebula, the rings of Saturn, the tails of comets, noctilucent clouds, the dust in the moon, plasma processing, all the way to fundamental physics, you can find dusty plasmas everywhere in the universe. And that's why the Department of Energy and National Science Foundation kind of helps us to study them. Next, please. And yeah, so I already kind of take that a biggest challenge for us to go human lunar exploration is the amount of dust that comes in the bodies of the the space suits. And so we are trying to mitigate them. And again, from plasma processing, which gives us these, to fusion devices. In the next slide, it is like that the tails of comets, rings of Saturn, protoplanetary disk where stars are born. Everywhere there is dusty plasma. So we study dusty plasma in our lab. But you might say, the next slide, please. Like, how can we use it, or what can we do to high school students, middle school students? Is when the dust is suspended, and like as you saw in that picture from our lab, the dust is not going anywhere, it's there. So that means it's very simple. Newton's laws can be actually studied. You can study dust using Newton's laws. If you did not have anything else, a little dust particle, which is a heavy thing, will just fall due to gravity. Why is it not falling? The Newton's laws must be using, so there must be an upward force. And so next slide, please. Yeah, so basically we can show a very nice little demonstration. It would be a little loud, excuse me. But you can take a ping pong ball. Well, in this case, what we got was a beer pong ball. So I got flack from the university that why am I buying beer pong balls for the lab? But it's a nice little demonstration. Everybody has a hair dryer and a ping pong ball, right? So it floats, and right, and you can actually I can move along with it. I can play around with it. So this very same concept that forces can be balanced, and according to Newton's law, if all the forces acting on a system is zero, you can stabilize something. And we use that all the time in dusty plasma physics. So something very simple that you can demonstrate in the class can actually help us do a lot of like real cool cutting edge physics with it. So with that, I think I'll stop.